So tutorial 2 is very similar to tutorial 1, just at a very high Reynolds number. As you guys recall, in tutorial 1, we had the Reynolds of about 250, and this time, you know, as you will do this maybe later on, experiment number 7, which will say that from 0 to 2000 is laminar region, 2000 to 4000 is transitional, and above 4000 is considered turbulent. That's why we have to have a value of above 4000 to be turbulent. So we will see now what is going on exactly. We will have the exact same geometry. We will solve it, but at different dynamic viscosity. And this is how we will control the Reynolds number. We see here we have the density is equal to the same, and the diameter same, length same, but the viscosity will be different. This will give us this value of Reynolds number 12,000. Here we see the velocity is same, as you guys recall from the previous report, and this is the dynamic viscosity. Now we can solve for this. Let's calculate it. Let's calculate the Reynolds number. As I mentioned before, let me just remind you, it's rho Vd over mu. Density times the velocity times the characteristic length divided by dynamic viscosity. So here we know we have the density of 900 multiplied by the velocity of 6.366. The d is 0.2, 0.009. Let me check. 0.09, and the diameter is 0.2. Let's see. We get the value of 12,732, which is exactly same. So for the above value of Reynolds number, the flow through. So we'll use the ANSYS to solve this different problem. Let's open up. I had it previously saved. I already tried the simulation and it works, so today it should go smoothly. So guys, you used before the same workbench and you created the laminar part, right? So since we will use the same geometry, what you can do is you can drag the fluent and put it here, okay? You can name this as turbulent, and since we have the same geometry, you can drag the old geometry into the new one. And by this, it's, as you can see, it's now having a check mark, so it's fully transferred, and you can modify that even as however you want. But this is a faster way to do it. But for you guys, I will start again with that. I will do the steps again just for demonstration. As you know, we will use space claim instead of design a modular because it's much more advanced and has higher capabilities. So let's start. Let's open it. As you know, here we mentioned the length is 0.2 and sorry, the length is 8 meters and the diameter is 0.2. But since it's a circular pipe, we will this is a 3D pipe, correct? But in simulation, as I mentioned before, we want the highest efficiency. We want to reduce the size of the problem. So what we will do is that we will make it a 2D, just a rectangle to represent the pipe. But since it's circular, we can even simplify it more by taking only half of the cross section. So this is what we will simulate. We will only simulate the upper half. So top we will have the pipe wall, and below we will have the axis. This is the axis of rotation. This axis of rotation will the rectangular cross section will rotate around it, and once it rotates 360 degrees, we will create this pipe shape. So once you open, you click return to 3D mode, and we will work in the X, Y coordinate system. So we'll create a plane there, and then we click here to go to that view, and then let's sketch a rectangle. The length is 8 meters, so it's 8,000 millimeters. And we know that the diameter is 0.2, but since we're taking only half, so it will be 100. Press enter, and you got this. I create return to 3D mode. Let's zoom extent. We'll see we have a perfectly normal rectangle. Then we'll close it. Make sure to switch the analysis type from 3D to 2D. And then let's open up the mesh. In terms of the mesh, we will follow the same procedure as last time, but we will have slight modifications to the bias of the mesh. So you cannot use the exactly same solver as last time, only the geometry. The mesh will be different. In terms of the mesh, you guys follow what I'm doing, and now I will show you. Let's wait for it to fully open. Here it's mentioned that we will do the same number of divisions, 130, but different bias type. And in the end, we will have 3,000 elements. So we have to make sure of this. We will check this, of course, when we do it. First of all, just generate random mesh to see what's happened. As you see, this mesh is considered very coarse. Coarse is not good. See, we only have like 20 elements. 20 elements will not be able to fully solve the problem. So that's why we have to modify it and make it finer. Coarse is bad and finer is higher quality. So let's apply face meshing. This tells us that it's mapped structure. Then we apply sizing. We click here to switch to edge selection. We click the top and bottom. And then here we have number of divisions, 100, as per the tutorial. Capture curvature, no, will make it the behavior hard to just follow orders. See, we should have 100 elements to in this y-axis. So then we'll do zoom to selection. Oh, sorry, I mean zoom here, and create another sizing. But this sizing we will only do it for this part. Apply it, make it number of divisions, and 30. Capture curvature, no. Behavior is hard, and we will do a bias type. Let's check this one. Here says that once we do the axial sizing that we just did 100, we will do the radial. For the radial, we will choose 30 divisions and then set bias type is like this. Now, and bias factor will be 10. Let's check it. Bias type is small first and then large, correct? Small first and then large. And the bias factor is 10. Let's check. Generate the mesh. It said here it's error because still we did not finish it fully. Let's zoom to fit and create another edge size to the right side. Let's do this exactly same number of divisions, 30. Capture curvature is no. Behavior is from soft to hard, and the type for the right side will be big to small. Let's do this, and the bias factor is 10. Let's generate. It was able to mesh it, and let's check if it's correct shape. Yes, it's correct. Top is very small, finer, and bottom is coarse. What we just did, this is called inflation layer. That at the wall we care about the boundary layer representation. That's why we want more finer element size there, but we don't care about here. Here is axial axis, so it doesn't matter much. Nothing is big going on here, but a lot of physics is we are concerned with up there. So this is basically to accurately resolve the boundary layer separation due to the slip condition. As if we go up backward here, let's check this size. Yeah, it's correct. Top is coarse. Sorry, top is fine, and this one is coarse. Let's check the number of elements. We have 3,000 elements. So far everything is everything is going on smoothly. So let's now next we will create names. These names will taken by ANSYS, and it will apply it as boundary conditions. This top is pipe wall. Of course, I will follow this pipe wall, center line, inlet, outlet. Let's go bottom. What was it called? Center line. Left is inlet. Right is outlet. Let's check. Pipe wall, correct. Center line, correct. Inlet and outlet. If you create, for example, pipe wall to be this one and this one, you will get an error. It has to. You cannot like overwrite names with this, and I think this is good because it will be a reality check. Like something is wrong, repeat it. So now we generated the mesh. We will do update to transfer it from mesh to Fluent. We finish from here. Let's close it. Next up, we have the setup, the physics part. It's same like last time. Let's open the setup. Will give us select double precision, and in terms of number of cores, I have 4. I have 4 cores, but like virtual total 8, but I just will use 4 for now. Of course, depending on your computer, like like HPC for Khalifa University has 192 cores, so this is it will be very fast. But for our application, it's not very computationally expensive and will be solved very quickly. Let's wait for it to open. As I mentioned previously, that like ANSYS is considered like slow in this field because it's like a collection of programs. They are all communicating with each other, but not perfectly. So this is a planar. This is axisymmetric. It's a rectangular cross section that rotates around an axis. So we switch to axisymmetric. We go to modes and then change it from here, the viscous calculations. Before we set it only as laminar, but now it's turbulent, so we'll use K epsilon model to solve it. Those values are from literature. The researchers find which is the best calibration for it, and they publish this, and ANSYS takes the results. This is normal. So let's check. We need K epsilon standard K epsilon model enhanced wall treatment. Okay. K epsilon standard correct enhanced wall treatment. None, 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 and yeah, leave everything else as it is. Okay. In terms of materials, we will modify. We have oil. The density is 900, while the viscosity is equal to 0.009. Correct? Yeah. 0.009, change, overwrite it. Let's go to boundary conditions. Here the center line is considered an axis. The inlet is a component, and now it will be like magnitude components, the axial and radial. Radial we have no velocity, but in axial we have 3.6, 0.6366 here, as mentioned. And then for the turbulence, we will set intensity and hydraulic diameter of 1%, and the hydraulic diameter we have it as 0.2. Intensity and hydraulic diameter 1, and this is 0.2. Apply, okay. The outlet will be pressure outlet, and pipe wall will be wall with no slip condition. In terms of reference values, as I mentioned, like reference values is only good if you extract results from ANSYS. This is for the solution method, we will use simple second order. So let's make this simple and then second order. We go to monitors, and the residuals is same as last time. We'll have e to the power minus 6. This is the error value that the solver will keep solving until it reaches. Before we had here xy, and I think it was xy, continuous xy, and here a single value. But now we have k as well as epsilon. So let's do standard initialization to make everything 0 and tell the solver what's going on. If you rerun the simulation, you have to initialize each and every time to delete the old results. But if you continue, if you want to run it, for example, like 1,000 time steps, but this is beyond this scope of this tutorial. With more, you just not initialize and keep running the code. We initialize now. Let's do just check. We have here I did check for number of elements. We have 3,000 elements. It's correct. Let's check the case. It says check your mesh. Let's general check. Before mesh check done. Is there realizable k epsilon? Yeah, okay. He said that k epsilon standard model is not very correct, but yeah, this is what we want. He gives suggestions only. So we'll set to 1,000. Let's check if everything is correct. Convergence 1e to power 6. Initialization, and then running. So let's calculate. We see that in the literature, they run it and they get convergence of the results. As we see here, 9.8 to the e minus 7. It reaches the minus 6 target. So the solution is stops, and there's no need to continue any further. Let's wait for it to run. During this time, if you guys have any question, you can please ask me. Also, did you guys submit the report for ANSYS tutorial 1? Good news. Also for report number 2, it will be similar template. So please use it, the one that we shared with you guys. Exactly same, but the material properties will be different, but same interpretation of results. There will be pressure, velocity, maximum, and distance to convergence, as well as skin friction coefficient. You will solve it exactly same. You get it from the simulation, and you will compare with the analytical solution you got from the actual equations. So follow the same template for it. Okay, guys? Let's see what happened here. We see that it ran to 205 iterations and it reached the target, so it stopped. Calculation is complete. Let's save everything. Here in the results, as I mentioned, it's same like last time. So now we'll move to show those big velocity vectors and velocity contours. After we save, we can exit. It's fine. See, ANSYS always does the check mark. So we see that we finished the setup and the solution has been transferred. And now we go on to the results. Double click it. You will see on the left side starting. So once you double click it, if you see it starting, it means it's working. Do not keep clicking it, it will lag. Let's go to the z-axis and let's see what we want to view. Velocity vectors. Let's create those. Let's create a new vector. Let's call it velocity vector. And its location is the periodic. Create. As you can see, they are too big, so we go to symbol and make them like 10% of the size. Let's move. As you can see, initially they will all have the same velocity, but wait, let's click here and then reflect mirror. Okay, the normal in the minus. So we see that they are all, this is the pipe, we see that initially they are all same length, but then the boundary layer effect, because at the wall we have no slip condition. No slip condition means the velocity is 0. So here the velocity we have is 0. As you can see, if we come closer, here we have a blue line and the dark blue is 0. So as we can see, as further we move throughout the pipe length, we see that it reaches a more stable shape, and we have this boundary layer formation. As you can see, then it converges. It converges after a specific time. Here we see at the very end, it's coming out the same. So this is the velocity vectors, and then we'll create the velocity magnitude contours by doing this, velocity magnitude contours. We'll do the velocity magnitude location at the periodic. Wait, let's hide this. Yeah, let's apply this first, and then hide the old velocity contours. We'll see only this one. As you can see here with the velocity contours, let's move in closely. We see how initially we didn't have a boundary separation, but after it moves for a while, it is formed. Let's go to the end. See, fully formed, fully converged. Let's create a video. The video needs streamlines. So now we'll just call it this streamlines. Start from inlet, equal space, number of points 25, it's fine. This one. Let's move in. Sorry. You can see that those are streamlines for the velocity. To view it more better, let's create an animation. The animation here, we click streamlines and then we'll make it slow. You have to disable this infinity. If you make it infinity, you will crash. So let's run it for only one repetition. You see here, it has like we mentioned, we set it up as like this spheres. And then let's make, okay, let's just show. We see that the ones closer to the boundary are very slow, but at the very center they are same velocity and they all move together. Okay. I hope it doesn't crash. Yeah, the problem with this animation is always it crashes. So I hope it didn't crash. Did it? Yeah, best to not try the animation. I only tried it to show you guys. It's not required in the report. So yeah, let's wait for a while. Is it? Sorry guys about this. Yeah, just ignore ignore this. Now you don't need to create this new results. We can results from same. Maybe I have to close this. Yeah, this is the problem with ANSYS because it's a collection of software, so they are always lagging. They're not talking good with each other. So let's create the qualitative results, sorry, quantitative results. Create a center line. Its location is from 0 to 8, and number of samples is 100. We apply it. It's at the very center because we closed this. It got removed. Wait, let me get back the center line. And then we will create a chart. It will be called axial pressure variation. Axial pressure variation. Data series is center line. The x-axis will be the x displacement and y will be the pressure. Let's apply it. So you see, we have 250, and throughout the pipe, which is 8, goes to 0. Let's check the results. 250 to 0. So let's export this results. It's axial pressure variation, but for turbulent. Those are the old results from the simulation. The old one. Let's check our result. Exactly. We see 2519. So it will be 2519. So 25149. So here we see that we get similar close to results to the simulation, but the theoretical is 233. So you guys need to compare with the theoretical by getting it from the equations that he is doing now. So, and then calculate the absolute percentage error, and you have to include this in your report. Okay, moving on, we go on to the velocity profile at the outlet. We create a line, data line at the end. A line called pipe outlet. It goes from 8, and 0 to 0.1. I will make it here 10 samples just to show you guys something. That when we create a chart, it's called outer velocity profile. Outer velocity data series. It will be pipe outlet. The x-axis will be the velocity magnitude, and the y-axis will be the y length. You see, we get very coarse results. We see here sharp edges. That's why when we go to pipe outlet, we increase the number of samples. We see here apply. You see how it became much smoother. The more samples, the smoother. But of course, it's related to the mesh. This is the smoothest we can go. See here we go to from 0.1 to maximum 0.75 almost. Let's check with the simulation results. Here we got, yeah, here we got almost 0.75. So here we're around 7.578. So let's of course we can go to here at velocity and export it, same as last time. At velocity profile, turbulent, and then we know the exact value. The exact value at y equals 0. You see 9.999. Here we got 9.999. Okay, here we got 7.5. Wait, that so this is the maximum velocity along the center line. So why did we get like different value? Sorry, this one is the velocity and this one is the y. So at y is 0, we get this value 7.5785. 7.57, yeah, it's exactly same as them. And of course, unfortunately here it doesn't mention, but you have to guys do same as laminar. Let's sorry, let's check. Here before we had analytical equation to create the velocity profile. Maybe it's not applicable here, but here, as we mentioned, like theoretical equation for centerline velocity is given by this value. So you had to compare with this. So please do this and tell me the results, because maybe this equation is only applicable to laminar, and I think it's not applicable to turbulent. So check, guys, apply this equation as well to turbulent, and if you get accurate comparison, that means continue. If it's not compared, then please tell me, and I will cancel this comparison part. But you still need to get the value. So yeah, this is this part. Moving on, we need to visualize the profile for the center line velocity. Let's close this, create a new chart. Let's call it center line velocity. Center line velocity. It's at the center line. The x-axis is the x displacement, while y is the velocity. Let's see the value. We see goes up and reaches on 7.6. This is same as the literature results, sorry, the tutorial results. So let's get the exact number. We see here it converges at this point. So again, you can here in tutorial number 2, we see that the maximum value it reaches at 6 is equal to 2.83 meters. Then it reaches a constant value at 6.38. So you guys need to, let's export this. It will be center line velocity turbulent. You guys need to find this value, the maximum value and the convergence value. Let's check. The maximum value, here we have x and this, let's see, 7.6, 7.6, 7.5, 7.8, 7.58. Yeah, so I think the maximum value here was 6.2, 6. Yeah, here is 6.2, I think. 6.21, 6.211 is 21822. Yeah, this is the maximum value. It's at x is equal to 2.828. It's 2.828. It was rounded up to 2.83, so this is correct. It converges at, let's see when it converges. It's 5.8, 5.8, 5.7. Seems to converge at 5.7. Here we see 7.9, 7.9, 7.9, 7.8, and then 7.8 is continues at 6.38. Yeah, this is correct. But we see here an old one, old summation. We also had a theoretical way to find it. Or no. There was no theoretical part for this. So include this point and compare your results. Lastly, we'll do the skin friction coefficient. Let's close this, and I think we are done with this. Of course, if you want to extract a picture, you go to File, Save Picture for this one. I think you can do a screenshot, it's fine. The best thing you can do is extract the result in CSV format, comma separated, and plot it in Excel for consistency. But of course, it's fine. Let's close this. Go back to solution, not setup, solution. We have now the last thing is to extract the skin friction coefficient. Let's wait for it to open. Then we go to plots, XY plot, create new. Wall fluxes, skin friction coefficient at the pipo plot. We get this value. He got around 0.008. Yeah. He got a value of 0.0079. Let's do write to file, export this results. Skin friction. It's saved in DB0, FF3, Fluent. Escape questions. Let's open it as a notepad. We see the X at 8 meters. As you can see here, it's not written in order. This is so you have to go with 8. So when you plot this, make sure to sort them from smallest to largest. Here we have 8 is 0.079, 0.7906, 03. We have slight error, but of course, compare with the analytical solution, we got here 0.008, so he got a value of error percentage of 1%. This is acceptable. So this is the end of this tutorial. Do you guys have any questions or anything? You should be able to use the same workbench. It's fine. Yes, Adam?
Doctor, the application sometimes it closes randomly, like one part of the application. Like I was doing the results an hour ago, and it just closed randomly, and I'd have to open it up again. It doesn't save anything. Do you know the issue?
The share screen or what?
No, not you. I mean the ANSYS for the what's it called? The results or results. Sometimes when I make a chart or a table or a line, it just closes. I have to open it again. Is there an issue?
Yeah, it's like you have the student license?
Student license, huh?
I think, yeah, this is crashing. Maybe like your laptop is the university laptop or what?
No, بس حتى الستودنت license it doesn't let you use more than 4 cores. If you use more than 4 cores, the application won't start.
Yeah, so like the student license also is limited in number of elements of the mesh. So you should like do the simulations in like follow the guidelines they mentioned. Less number of mesh, 3,000 elements. You should have 3,000. In terms of number of cores, yeah, make it 2 or 4 maximum. In terms of crashing, yeah, this like happens usually with console. I was showing you guys and crashed with me. So the results. So this happens. Yeah, it's not your fault. So just like power through it.
Thank you.
In terms of the results and like, were you guys able to for the report one extract all the results and simulate no problem?
I did some of them. I'm gonna continue after the lecture, but it was fine. It's just sometimes it would crash.
Yeah. Okay. In terms of group, you guys are allowed 2 people per group, or you can work individually. It's up to you. So, like, if you have any other questions regarding the results or anything, you can tell me. The code, this one is like you can do a trick here. If you already did the laminar, you can do a duplicate for it. You can duplicate it entirely, but then only go inside the mesh and modify it. And the setup just learns from laminar to k epsilon. So like if you are comfortable with tutorial 1, which is like you are like you will easily do tutorial 2. It's really same